Last week, the machine learned to keep its tokens alive. This week, we lock down what those tokens can touch. Because right now, any query can read any row. The only thing standing between one user's data and everyone else's is a where clause somebody remembered to write. So we move the rule into the database itself. Row-level security, policies that scale, and the one policy shape that quietly recurses until Postgres gives up. Here's where we are. Data layer, OAuth, token store, all lit. And the box we flickered at the end of last week, row-level security, ignites today. By the end of this video, the database itself will decide who sees which rows. Every query the route handlers send into the data crosses that row's boundary, and no client can go around it. But there's a trap on this road. The most natural policy you'll ever write, recurses forever. We're going to walk straight into it, and then straight back out. Start with the way most apps do this, and the way it leaks. Your post table holds everyone's rows, and every query filters, where a user equals the current user. It works, but notice where the rule lives. Not in one place, in every single query. The dashboard query, the search endpoint, the export job you'll write 6 months from now at midnight. Each one has to remember the filter, and one day, one of them doesn't. A new endpoint, a quick admin script, a join that pulls the table in sideways. No where clause. Nothing errors. Nothing even looks wrong in review. The endpoint just quietly returns everybody's rows to anybody who asks. That's the shape of the leak. The data lives in one place, but the rule protecting it is scattered across the whole codebase, and its safety depends on nobody ever forgetting. A check you have to remember is a check that will, eventually, be forgotten. So move the rule to where the data is. In Postgres, and Supabase is Postgres, you switch on row-level security for the table, and from that moment, the table denies everything by default. Then you grant visibility back with a policy, a predicate the database attaches to every query against that table. The ownership policy is one line of intent. A row is visible when auth.uid equals the row's user column. Auth.uid is Supabase reading the caller's identity out of their signed token, so the database knows who's asking on every query without your app saying a word. Now run the leaky endpoint from the last chapter, the one with no where clause. It returns only the caller's rows anyway, because the database quietly appended the filter itself. You cannot forget a check you no longer write. And name the trade out loud, in the tradition of this season. Enforcement just moved into the database. One place, always on, and we'll pay for that centralization before this episode's over. Now the trap, and it starts with a completely reasonable feature, teams. A members table says who belongs to which team, and the policy you want is, you can see the members of teams you belong to. So you write it the obvious way. This row is visible if there's a row in members linking you to the same team. Read it back, it sounds right. But look at what the database has to do. To decide whether you can see a row in members, it runs a query against members, and that query is subject to the same policy, which runs a query against members, which fires the policy again. There's no bottom. Postgres detects the cycle and refuses, with error 4, 2, P1, 7. Infinite recursion detected in policy. Here's the mental model that makes this obvious forever. A policy is a gate on a door. To decide whether the gate opens, it can look at anything it likes, except through its own door. The moment a policy needs its own table to answer, you're in the loop. The way out is to answer the membership question somewhere the policy doesn't reach. In Postgres, that's a security definer function. Normally, a function runs with the permissions of whoever calls it. Same rules, same policies. A security definer function runs with the permissions of whoever defined it, the owner. And the table's owner isn't subject to its row-level security. So you write one tiny helper. Given a user and a team, is this user a member? It reads the members table as the owner, outside the policy's jurisdiction, and returns a yes or a no. The policy stops querying the table and calls the helper instead. The loop is broken. The gate asks the helper reads freely, done. But hear the new trade because it's real. You've just created a function that bypasses row-level security. That's a sharp tool. Keep it tiny, one question, one answer. Pin down who owns it, don't let it grow arms over time, and treat any edit to it the way you'd treat changing the locks on the building. Powerful and audited, or not at all. One more thing before we zoom out, because this is where teams turn RLS off in frustration. Performance. A policy isn't magic. It's a predicate the database evaluates per row on every query that touches the table. Run explain on a query against a protected table, and you'll see it sitting right there in the plan as a filter, exactly like a where clause you wrote yourself. And that tells you how to make it fast, the same way you make any filter fast. Index the columns the policy touches. The user column, the team column. Without the index, the database checks the predicate row by row across the whole table. With it, it jumps straight to the rows that can pass. And keep the caller's identity from being recomputed for every row. Wrap that call in a subselect, so the planner resolves it once per query, not once per million rows. Treat the policy like a where clause you happen not to write, because to the planner, that's exactly what it is. So name the trade, out loud, like every box on this map. What you bought. One enforcement point in the database that no client can go around. Not the dashboard, not a leaked API key, not the endpoint someone ships at midnight without the where clause. The filter is on the table, and the table is the only place the data lives. What you paid. Visibility. The rule is invisible in your application code now. A query that comes back empty looks exactly like a bug, until you remember to go check the policies. Debugging means thinking in 2 layers. And the planner pays a little on every query, which is why we index the predicates. That's the deal. Some debuggability and a bit of query cost, traded for a security boundary that doesn't depend on anyone's memory. On this machine, multi-user data on the public internet, that's a trade you take. Step back and look at the map. The rows boundary is lit. Every query from the root handlers into the data now passes through row-level security. App checks leak, the rule moved into the database. The caller's identity against the row, appended by the table itself. The team policy recursed? Because a policy can't query its own table, so a tiny security definer helper answers membership from outside the loop, kept small and audited. Policies slow? They're just filters to the planner, so we indexed what they touch. The data guards itself now. Which raises the next question. What should the outside world be allowed to call in the first place? Next week, the API surface, server actions versus root handlers, and the one rule for choosing between them. See you Wednesday.